So I'm going to go ahead and take this problem from start to finish. I want to find all critical values. I want to find the relative min, relative max, concavity, points of inflection, and then I want to go ahead and sketch it. So we have a lot of work ahead of us. Finding critical values, that is going to be taking the first derivative, but since I'm going to be talking about concavity also, I'm going to go ahead and just fire out the first derivative along with the second derivative, just so I have it in a nice organized space here. So the first derivative is going to be 3x squared minus 6x plus 3, and 9 is a constant. Second derivative is going to be 6x minus 6, 3 is a constant. So there's our derivatives. One spot, that way we're not having to look around everywhere. Next, I'm going to start with critical values. So my critical values are when my first derivative is set equal to 0. Or where we can't take the points on the graph where we can't take the derivative. But we don't have to worry about anything here in this graph, or in this function. So we don't have to worry about that. All we have to worry about is where the first derivative is going to equal to 0. So let's set our first derivative equal to 0. 3x squared minus 6x plus 3 equal to 0. And whenever you have a quadratic like this, you want to factor it, but before you do that, try to see if there's something that can be factored out just to make your life a little bit easier. And there is. 3, 6, 3, I could take out a 3. So I'm going to factor out a 3. I'm left with x squared minus 2x plus 1. 3 divided by 3 is 1. 6 divided by 3 is 2. 3 divided by 3 is 1. Equal to 0. Now I'm able to factor much easier. I don't have to sit here and worry about doing 3 times 3 and add up to negative 6. I can just worry about two numbers that multiply to a 1 and add up to a negative 2. Multiply to a positive, add up to a negative. Multiply to 1, 1 and 1. Want to add up to negative 2 though, so it's going to be negative 1, negative 1. 3 is a constant, so I'm not even going to bother with that. X minus 1 equal to 0. So we just get x equal to 1 for our critical value. X equal to 1 resets. X minus 1 equal to 0. We get x equal to 1. So x equal to 1, let's go ahead and plug in 1 into our original function just so we know what we're dealing with here, like where this is actually going to fall on the graph, where this critical value is on the graph. So I'm going to take 1 and I'm going to plug it into the original function. So this is going to be 1 to the third minus 3 times 1 squared plus 3 times 1. And this is one that you probably could just do mentally, but it wouldn't hurt to plug it into your calculator just to make sure. It's something that we don't want to make a mistake on. So 110 is our critical value. So right here. What that means is that the graph is doing something there. It is flattening out. So that means it could either be doing this, it could be decreasing, and then going increasing. It could be increasing, going to decreasing. It could be increasing, increasing, decreasing. It could be something is happening to this critical. It's flattening out in some way. We just now need to figure out what's happening to the left, what's happening to the right, and we also want to grab some points of inflection. So while we're talking about the first derivative, let's keep working off of this first derivative. So I'm going to set up some intervals. I just have this single point of this critical value. So I'm going to go from negative infinity to 1. It's a really bad infinity sign. I'm going to go from negative infinity to 1, and then 1 to infinity. So now we want to take some points in this interval and test them. So I'm going to take f prime of 0. 0 is in that interval, always fair game. Love that, love using 0. F prime of 2. So plugging in 0 into our first derivative. So here's our first derivative right here. 3 times 0 squared is 0. 0 minus 6 times 0 is 0. 0 minus 0 plus 3. 3 is a positive number, indicating increasing. So we know it's going to be doing something like this, increasing. And then what's happening on the other side of that? So we're going to do f prime of 2. So we're plugging in 2 into the first derivative. 2 squared is 4. 4 times 3 is 12. Minus 6 times 2. 12 minus 2. Or 12 minus 12 is 0. 0 plus 3 is 3. Greater than 0. It's positive, so that's also increasing. So it's doing something funny. It's increasing, flattening, increasing. All right. So we have a pretty good idea what this graph is going to look like now. So we did critical values. Relative min, relative max, we'll talk about that at the end. Concavity now. So let's work off of the second derivative. So second derivative is 6x minus 6, and I'm looking for points of inflection right now. So we want to set our second derivative equal to 0. I'm going to solve this at 6, 6x equal to 6, 6x equal to 1. So at x equal to 1, we have a point of inflection, and we're indicated that that is 110 was the ordered pair there, 110, because that was our critical point also. So to determine concave up, concave down, we want to work off of those same intervals, negative infinity to positive 1. And the reason I'm saying same intervals is because the critical point was also the inflection points. So negative infinity to 1, 1 to infinity. So negative infinity to 1, I want to take a point in that interval, plug it into the second derivative. Same thing over here. Second derivative, take a point. So I'm going to use the same ones, but now we're plugging in the second derivative. So I'm going to have f double prime of 0, plugging in 0 into my second derivative. Second derivative is here. 6 times 0 is 0. 0 minus 6 is negative 6. So that's a value less than 0, indicating concave down. So plugging in 0 into the second derivative there. Plugging in 2, positive 2, into our second derivative. 6 times 2 is 12. 12 minus 6 is positive 6. So that's a value greater than 0, indicating concave up. So on the interval from negative infinity to 1, we have concave down. And then from 1 to infinity, we have concave up. And we also have increasing to increasing. So what that's going to look like then, and here's how we sketch this, and point of inflection is right here. So what that's going to look like then is this. And you could get pretty precise. You could grab a couple x values. But just to save some time on this video here, we're just going to go ahead and sketch this out. So it's going to look something like this. And I'm a little off. It should be a little bit closer there. But then it's going to flatten out and then go out. So it just flattens out for a split second. And then it goes out that way. So then that would be our graph. So critical values located here. Relative min, relative max. Oh, I think I'm going back through. I didn't talk about that. So talking about relative min, relative max. We do not have any. That's right, none. No relative minimum, no relative maximum, because we're not doing any sort of increasing to decreasing, back to increasing or anything like that. It's just increasing, flattens out, then back to increasing. So we do not have any relative extrema here. Concave up on, concave down on this interval. So from here to here is concave down, as we indicated right here. Negative infinity to positive 1 was concave down. That's why it had this curvature going in like that. Then concave up, so I had that curvature going like this. So there's our sketch, point of inflection and sketch. Really good process to understand, really good problem to understand this process of going from start to finish on a function and pretty much being able to generate. Now I know I didn't do exactly every single thing. I probably could have taken a couple x values to get an exact idea of where this is coming in from, but that would make this video a little bit longer. I'm just trying to keep it relatively short, so that's about what it's going to look like.